When you can't solve a problem and you don't know what to do, watch this video to understand 1509 minimum differences between largest and smallest values in 3 moves. Okay, pretty short description. These are the kind of problems that can often be quite misleading because you think, oh, short description, probably simple solution. But sometimes the most difficult problems have the shortest, most concise descriptions. But that's completely irrelevant. So you are given an integer array nums. Cool. In one move, you can choose one element of nums and change it to any value. All right. So I can take the array, I can look at a number like 4 and change it to 6 or whatever I want to do. Return the minimum difference between the largest and smallest value of nums after performing at least 3 moves. So we want to return the minimum difference between the largest and smallest value. So what does that really mean? We want to get the values to be as close as possible to each other, right? And we can change these values by changing any one value within the array. So we're probably going to be changing the smallest thing and the largest thing, right? If you have numbers all over the line, right? 5, 3, 2, and 4. I guess one way of thinking about this, right, is if you had this number line like this, right? And then you had 5, 3, 2, and 4. So this is at 5 spaces. So maybe I'll label these like so. Right. And then you had these values that we're assigning. So there's one value at 5, right? There's one value at 3. There's one value at 2. And there's one value at 4. Okay. Now, we're trying to return the minimum difference between the largest and smallest elements values of nums after performing at least 3 moves. Well, what we want to do is we want to get them as close as possible, right? Because right now they're 3 away, right? The length of this, right? You can think of it as the length, right? It's because it's the difference between the largest and the smallest element, right? So the length of this system here right now is 3, okay? But we could technically take these elements, right? And we can kind of scrunch them up, right? Because I can choose one element of nums and change it to any value. So what that basically signifies is that I can take this 2, instead of it being a 2, right? And I'm going to recreate this array here just so you have kind of a pictorial representation and, a actual written representation of the array, right? I can take this 2 and say, you know what, I'm going to scrunch it up, and I'm going to take this 2 and I'm going to change the value, right? I'm going to take this 2 and I'm going to move it to 3. Right, and that's one move, right? I can do the most number of moves I can do is 3. So I could take this 2, convert it here, or let's just say I take this 2 and I turn it into a 4. Right? There's multiple solutions of the way you can do this, right? And I say, okay, I'm going to take this 3 and move it to 4 too. Right? So I scrunch this value over here, and I'm going to take this 5 and also move it to 4, and that's 3. That's 3 values that I've now since moved. All right, and now they're all 4. I can move them all in, and we're good to go. Okay, and that's where you get the value 0. All right, that's one such example. Not the most involved. You can kind of see that, you get the 0. It's kind of like an edge case or base case. I don't know how you want to look at it. So maybe it's not the most revealing. So let's look at maybe something else here. Let's look at 1, 5, 0, 10, 14. Okay, so that's going to require me to so now I have these new sets of points, right? And again, I'll actually create the entire array. So we have 1, 5, 0, 10, and 14. All right, and I'm going to place all these on the number line. So I have an element at 1. I have an element at 5, I have an element at 0, and I have an element at 10, and I have an element at 14, right? So now the distance between these things is, far greater, right? We have something all the way at 0 and all the way at 14, right? And then we have this kind of space between, so that creates a space of 14 in between. Right? So now we're trying to scrunch these things up together, right? Now, I guess the first observation, right, the main observation, which is pretty intuitive, and if you didn't, notice this, don't criticize yourself, but just recognize that, well, if we're trying to get these things closer together, right, you want to scrunch them together, right? You can kind of imagine, the idea is I want to scrunch these things together, right? And the distance between these elements, right, is defined by the thing that's farthest left, right, or the smallest element, and the thing that's farthest right, right, which is the largest element. Right, this distance, right, this 14 is based off the largest element minus the smallest element, right? And that's a direct definition here, right? The minimum difference between the largest and smallest value. So when we're thinking about, okay, how are we going to tweak values in order to try to minimize this distance? This value, right, 5, for example, right now at least, is irrelevant, right? If this 5 was over here, it doesn't matter where I put this 5. It's the distance is dependent on the largest element minus the smallest element. So the indication, right, is that we should probably modify the smallest element or the largest element, or since we can modify 3 things, maybe we modify some grouping of the smallest element or the largest element in order to move these things together, right? But trying to worry about these elements in the center is essentially a waste of time, because what is that going to change? Nothing, right? Only when I take this 0 and I move it over does this actual distance, right, this 14 distance, end up being modified. So that kind of limits greatly, right, what we actually need to focus on, which is always good, right? When you solve these problems, sometimes it's good to think about, how am I going to limit what I actually need to look at in order to find the optimal solution, right? Because I have all these elements, so what do I actually focus on and think about in order to solve this? So that's just something to consider. Okay. And what is the solution here? Well, right, again, we want to scrunch these values together, right? So we want to push them together. So there's multiple options, right? One thing is, like, the 14 is really far away from the other ones, right? So intuitively, if you look at this, okay, I'm going to move this 14 over. Now, do I want to move it to 10? Or I can move it anywhere, right? And I'm going to move it to the center, right? Because I want to make things as close as possible to each other. So I might as well move it all the way to the center. So I'm going to change this 14 to a 6. And I'm going to take this 10 and I'm going to move that to the center too. Move that to 6. And then I'm going to take this 1, right? I'm going to move it over to 6. And now the difference is max 1. Right, max 1. Okay, now the reason why, so, I'm really just trying to scrunch these things together, right? And I can only do it 3 times. But if I could continue doing it, I would take this and, move it there, and the difference would be 0. But I can only do it a maximum of 3 times. Since I can do it a maximum of 3 times, I'm going to take these elements and I'm going to try to move them in towards each other, right? But that is the optimal solution, but that doesn't mean there wasn't other options to consider, right? There's multiple things that you can do. Right, I could have also said, well, I'll move this 1 over and this 4 over and then this 16 over, but now I move those 3 over and the max distance is 4. So that actually wasn't the best option, right? There's different ways you can do this, right? But I guess the next observation you should make is, well, based on the first one, which is we only care about largest and smallest. The next observation is we can only move some combination of largest and smallest. And what does that mean? Well, in this scenario, right, I have 3 moves that I can make, at most 3. Maybe I don't need to make all 3, whatever. But I can make at most 3 moves. So what are my options? Well, I can move one of the smallest and the largest. So I'm gonna expand this out, and I'm gonna show you all possible scenarios. Okay, so there's how many possible ways can you do this? There's a lot of different ways you can do this, so I'm going to just iterate through all of them. So let's say I just decide to move the 3 smallest. So that would be this case. So if I move the 3 smallest, I'm going to try to move them to the center, right? Now, this is something you need to consider because, well, now this is the smallest. So if I move the 3 smallest, I remove this one to here, this one to here, this one to here. Right, that's my 3 smallest option, and that results in a difference of 4. Right, what I'm saying is, again, just to iterate what I'm doing, we only care about the largest and smallest because that's the only thing that's going to change my length. I can only move 3 things, so what if I just look at all combinations of 3 things I can do? I can move the 3 smallest, I can move the 3 largest, etc., etc., etc. All right, so now let's look at the case where I move the 2 smallest, 1 largest. I'm going to do 0 largest, 3 smallest, 1 largest, 2 smallest. And what I mean by that is I'm going to move the 2 smallest into the middle. Did this get changed? 1, 5, 0, 10, 4. Okay. I'm going to move the 2 smallest into the middle and the 1 largest into the middle. And that results in a difference of 5. So that's another way of doing this, and it's not the best, right? We'll move this 4 over here. All right, let's again now try the next thing that we can do. We can try to move the, what will be the next possible? We could do 2 largest and 1 smallest into the center. So we take this one smallest, move it to the center. We take the 2 largest and move it to the center. And that results in a difference of 4. Now there's only one other combination of things that we can do if we're just thinking about smallest and largest, right? Which is what we should be thinking about because changing anything in the middle doesn't really do anything for us. I don't need that. I need all right, I need this again. So let's do that one more time. I should have just put copy so I could continue pasting it, but sometimes you don't learn lessons in life. Okay, so this is the 3 largest and 0 smallest case. So in this case, we're going to move the 3 largest There was no 0 all along. Oh, this is a different problem that I'm solving because, oh no, there is 1, 5, 0, 10, 14. 1, 5, 0, 10, 14. Okay. So now I'm going to move the 3 smallest into the middle. Right, so I'm going to move this 5 here, I guess would be the middle now. All right, I'm going to move this and this here, and now my difference is 1. Right, so the point here is, well, there's only kind of 4 situations I can deal with, right? I can move the 3 smallest and 0 the largest, so I move all the smallest things over. I move 1 of the large over and 2 of the small things over. I move 2 of the large things over and only 1 of the small things over, or I move all the largest over, right? You can kind of basically think of this as like, I don't really know how else to kind of put this in terms you'd understand. But imagine you had a hand here, right, and another hand here. And all these hands are doing is they're trying to smush these numbers together, right? So this hand here is trying to push these numbers in, and this hand here is trying to push these numbers in, right? And you can only push 3 numbers, right? You can only change the value of 3 numbers. So you can only move 3 numbers over. So it's about deciding, you know, how much from one side do you want to push over and how much from another side do you want to push over. Now, another question you might have is, well, how do you know where to put them, right? You know which ones you need to move, but how did I know to put it at 10 or put it to 1? Well, It doesn't really matter where we put them as long as they're within the boundaries of the new edges, right? So when I had to push 10, 11, and 15, where it's like, I'm going to put them over to the next element where they're going to be, right? Because now it's within the boundary, right? I could put them in between. It doesn't really matter, right? It just matters where the new edge would be, right? If I'm trying to move these over to maximize the gain that I get, I should put them in between where they'd be in the new set, right? So since I'm moving 14, 10, 5 over, I'm going to put them in between 0 and 1, because once I remove, right, once these are eliminated, I want it all to be within this set over here. Okay. Okay. So that is basically all the cases that we have, right? We have the 0, 3 case. We have the 1, 2. We have the 2, 1. And we have the 3, 0. And they all have corresponding scores that you get, and you just return the minimum such of those scores. Okay. So how do we get to implementation here? Well, since we need to think about the largest and the smallest, you might feel inclined to say, oh, we should sort this system, right? We should sort the whole system, and then we have the smallest and the largest things we need to look at. But that's kind of overkill, because you don't need the whole universe in order to solve this problem. You just need to know the things on the edges, right? The smallest values and the largest values, some set of those values, right? Whatever's happening in between is irrelevant. So we don't need to sort the whole system, right? If we have a system like this, okay, let's just say we have some system of elements. I'm going to draw it like a cloud, okay? All we really need to know is like, okay, what are the smallest elements in this cloud and the largest elements in this cloud, right? And we're going to move things over, right? So when I solve this, I'm actually going to take these values and say, okay, I'm going to squish some combination, right? So I'm going to move this in or move this in, right? Or maybe I'll move these 3 in or these 2 in, right? But whatever's going on in here is just a big black box, and I do not care. It's irrelevant. Hopefully this point makes a little bit of sense. What I'm basically saying is, you know, since we can only remove 3 things, I can only push a maximum of 3 values, right? So I can only change the minimum 3 values or the maximum 3 values or some combination of them, right? But what's happening in here, I can't like modify those values. So I shouldn't really concern myself with sorting them. As long as I can get the minimum 3 things and the maximum 3 things, and then think about it in terms of those values, whatever goes on in here is kind of irrelevant, right? Because I can only modify these values on the left side and the right side, right? Like here, since there's only 5 values, right, there's no middle because there's 3 on the left and 3 on the right, because there's 5 is less than 6. But if there was like 100, let's see if there's a larger case. There isn't, right? If there's a larger case, let's just say we had, for example, just for the sake of trying to make this point clear, because it's probably not very clear, let's just say we had, you know, a system that looks like this. Okay, and the values in this system are 0, blue. Keep the color consistency here. So 0, 2, 3, 5, 7, 8, 10. Maybe there's 2 10s, 12, 13, 14. Since I'm only thinking about the smallest and the largest values that I'm modifying here, right? I can modify these 3 values to minimize my score, right? Because I'm trying to push things in, right? But after I modify these 3 and push these, right? After I move these elements over, I can't move this 5, right? This 5 is stuck because I can only move a maximum of 3, right? And same on the other side, right? I can only move a maximum of 3 of these elements before there's nothing else that I can do, right? So I can only push things in so much. So I don't need to concern myself with these actual values in here, right? These actual values are irrelevant, right? What's going on in here is more or less just a black box. It does not matter at all, right? So that's kind of the point that I'm trying to make here, right? So we don't need to sort this whole system. As long as we know the 3 minimum and the 3 maximum, we can move things in. But anything after that I can't change because I can only change a maximum of 3. So we don't need to sort the whole system. We just need to sort pretty much 6 things, right? So with that said, let's think about how we're going to do this, okay? So since we can change a combination, as soon as we get, we're gonna do n largest and n smallest to get the 3 smallest and the 3 largest. I'm just trying to think about how, you know, the edge cases in this can be kind of messy, right? And say, okay, we have three smallest, 3 largest. So let's say we have that, right? Let's say we have, you know, the 3 smallest A, B, C and the 3 largest D, E, F. I could change these 3 to the next thing in the system. So I do need to know what this next value is in order to change to it, right? Because if I remove all 3 of these, I'm trying to X out X's, right? The next smallest value would be here, right? And if I remove all 3 of these, the next smallest value would be here. So I need to know what these 4 values are, because if I remove these 3, this would be the next smallest. If I remove these 3, this would be the next largest, right? So I need to know E. I need to know what these 2 values are, x1 and x2. Right, so if I remove A, B, and C, right, that would be the difference of... So let's go through those scenarios in the general case, right? So for A, B, C, x1, x2, D, E, F. This case would be I remove the 3 smallest. So that would correspond to removing the 3 smallest. So my answer would be F minus x1. Right, because I don't need to care about whatever else is going on in the center, right? Even though in this case there isn't any center because there's less than 6 elements. In this case, I'm going to just copy this for all of them before I... All right. So that's removing the 3 smallest A, B, C. This next case would be I remove 1 large and 2 smallest. So the answer would be E minus C. The next one I remove the 2 largest and the 1 smallest. So the answer would be D minus B. And then the last one, I removed the 3 largest and 0 smallest, so that would be x2 minus a. Right, and that's pretty much what happens here, right? Because in this problem, we have 0, 1, 5, 10, 14. Right, so we have, let me write that again. So 0, 1, 5, 10, 14. So this would be 14 minus 10. I'm going to sort this. Okay, 0, 1, oh, it already is sorted. I'm an idiot. So this is 0, 1, 5. Problem is there's not enough elements to create it again, right? So there's space in between. So, you know, there's overlap because there's less than 6. So we'll call that, so 0, 1, 5, 10, 14, 14 minus 10. This would be the 1 largest minus the 2nd smallest. And so on and so forth. I'm not going to go through it, but I think you get the general idea, right, of how this works. So let's go ahead and do that. So let's find that, let's say S equals the n smallest. So we'll do heap Q n smallest. We want the 4 smallest because we can eliminate 3, and that last one would become the value if we were to keep it of nums. And then L equals heap Q dot n largest for of nums. And let's print out S and L. S and L. Ah, S and L. You ever seen that? Okay. So for this problem, it would be 2, 3, 4, 5, 5, 4, 3, 2, because there's no, it's too small, right? That's fine. let's just say that we'll create a new array nums equals s plus L reverse, because the largest will give you the largest, but from, in decreasing order. So we'll reverse that. And then we just play this game, right? So we say we return all of our options. We could do this the smallest to largest, meaning so we do the minimum of, well, we remove all of the smallest elements, right? So that means that the last element is what we keep. But I'm going to make that, should I just keep it in this form? Yeah, but then it gets a little weird. Right, so I keep the largest, but that would be, the largest would be at element 0 since this is backwards. Right, so this would be the largest. And then I remove the 3 smallest. So that would make this the element. So that'd be S at 0, 1, 2, 3. Right, I either remove one of the largest, so that'd be L of 1. And I remove 2 of the smallest, so that'd be S at 2. Okay. I remove 2 of the largest, so that'd be L of 2. This is L, so move 2 of the largest, that'd be L of 2. And I remove 1 of the smallest, so that'd be S at 1. Or I remove all 3 of the largest, so that'd be L at 3. And I remove none of the smallest, so that'd be S at 0. And this should probably increment, right? So this should go 0, 1, 2. So 0, 1, 2, 3. And it should decrease 3, 2, 1, 0. Okay. And there are probably some edge cases in this that I need to think about, but I'm not sure. Because this is a little bit cleaner than my original code. So I wonder if... yes, of course. So here the problem is, right, there's only 3 elements. So, well, the fact is if the length of nums is less than 4, you just return 0. Or less than or equal to 4, actually. Yeah. Because if there's less than or equal to 4 elements, right? If I have just something to think about before you go, right? If I have just 4 elements, if I have only 4 elements, right? A, B, C, D. Well, I can always just 1, 2, 3, right? I can always put 3 of the elements on the 4th one. However you want to think about it. Doesn't really matter when it's such a trivial case. So if I have less than or equal to 4, I can always put 3 of them, I can always put all of them except 1 on top of each other. Right? I can put all of them on the one I don't put it on, if you want to think about it that way. Okay, so what is the runtime and space complexity of this problem? So since we're only thinking about the largest and smallest, it really improves our complexity. So we say n is length of nums. Okay. For time, well, what do we have to do? We have to find the n smallest and the n largest. And you may say, well, that's like n log n, because you have to sort the array and find the largest and find the smallest. But the truth of the matter is you don't actually need to sort the whole array. You just need to make a heap, 2 heaps, right? You can look into the implementation of this, but basically you just have 2 heaps that are the size of the things that you want. So it only it's proportional to the size of the elements that you actually want. So when this is 4 elements, it's 4 log 4 operations. This is also 4 log 4 operations because it just creates a heap of that size, and then moves elements in if they're less than the minimum, greater than the maximum. Again, just look at the implementation. There's just understand, right, that a heap operation is proportional to the size of the heap, but the heaps that you create in order to find the n smallest and largest are only size 4, so that's constant. And then, well, we still have to go through the whole array to find the n smallest and n largest, right? So that's linear time, but the heap operations themselves are constant, right? So we have to look at all the numbers to create these heaps of size 4. So that would be n time, right? We have to do constant operations for all n elements, so that's n time. So this would be n time. This would also be n time, so that's 2n. And then this operation is just comparing 4 things, so that's constant time. So that would be big O of n time, right? And you can say, okay, this is n times 4 log 4, right? Because there's these 4 log 4 operations, but of course this is constant, so that's why it gets removed. Okay. And then for space, well, we create a heap of size 4 and another heap of size 4. It doesn't matter how large the input is. If nums is 10 elements, 100 elements, 600 million elements, we just do these heaps of size 4 and keep track of that. So that's constant space. All right, guys. Hope everyone has a beautiful day.